Welcome to Differential Equations. Almost every equation you have solved so far has asked you to find a number. Solve x squared minus 5x plus 6 equals 0, and you get 2 or 3 numbers you could write on a fingertip. Today we meet a completely different kind of equation, one whose answer is not a number but an entire function. A differential equation relates an unknown function to its own derivatives, to its own rates of change. Solving it means finding the function or functions that make the relationship true. Here is the headline example. The equation dy dx equals k times y says the rate of change of y is proportional to y itself. Its solution is the exponential function c times e to the kx. Not a value, a curve. Over this episode, we will define what an ODE is, classify equations by order, separate ordinary from partial, make precise what a solution is, distinguish general from particular solutions, meet the initial value problem, and see why this subject is the language of every science of change. Let's begin. Let's make the definition precise. A differential equation is any equation that relates an unknown function, call it y of x, to one or more of its derivatives. In full generality, we can write it as some relationship f of x, y, y prime, y double prime, and so on, set equal to 0. The first thing we measure about such an equation is its order. The order is simply the order of the highest derivative that appears. So y prime equals 2y is first order, because the highest derivative is the first derivative. Y double prime plus y equals 0 is second order, because a second derivative shows up. And y triple prime minus x times y prime equals e to the x is third order. Order matters because it tells you, roughly, how many arbitrary constants the general solution will carry, and therefore how much extra information you need to pin a unique answer down. As a preview, Newton's second law, mass times the second derivative of position equals force, is a second-order equation, because acceleration is a second derivative. Now, an important fork in the road. Differential equations come in two broad families. The first is the ordinary differential equation, which is what this whole course is about. In an ordinary equation, the unknown function depends on just one variable, usually time, or a single position coordinate. Only ordinary derivatives, the dy dx kind, appear. The second family is the partial differential equation. There, the unknown depends on several variables at once. Say temperature as a function of both position and time, and partial derivatives appear, written with that curly partial symbol. The heat equation, which says the partial derivative of temperature with respect to time equals a constant times the second partial derivative with respect to position, is the classic example. Partial differential equations are a richer and harder subject, and they are built squarely on top of the ordinary theory, so we earn the right to study them by mastering ordinary equations first. For the rest of this course, ODE means one independent variable. This is the conceptual heart of the episode, so let's slow down. A solution of a differential equation is a function, y of x, that makes the equation true when you plug it in, together with its derivatives. Not a number that satisfies it, a whole function that satisfies it at every point. Let's verify one. Is y equals e to the 2x a solution of y prime equals 2y? Differentiate, y prime is 2 times e to the 2x, and 2y is also 2 times e to the 2x. The two sides match for every value of x, so yes, it is a solution. Try another. Is y equals sine x a solution of y double prime plus y equals 0? The second derivative of sine x is negative sine x. Add y, which is sine x, and you get negative sine x plus sine x, which is 0. It checks. Notice something wonderful. Verifying a solution never requires you to solve anything. You just differentiate and substitute. Solving is the hard direction. Checking is always easy. When you actually solve a differential equation, integration enters, and integration always brings an arbitrary constant along with it. So you never get just one solution. You get a whole family. Solve y prime equals 2y, and the answer is y equals c times e to the 2x, where c can be any real number. We call this the general solution. A first-order equation gives one free constant. A second-order equation will give 2. Each choice of c is a different curve. Take c equals 1 and you get e to the 2x. Take c equals negative 3 and you get negative 3e to the 2x, a curve that dives downward. Take c equals 0 and you get the constant function 0, the equilibrium solution where nothing changes. A single one of these curves with c fixed to a definite value is called a particular solution. So picture the general solution as an infinite stack of curves filling the plane, and a particular solution as one curve plucked out of that stack. The natural next question is, which one? Here is how we choose the one curve we want. We supply extra information called an initial condition, a single data point the solution must pass through, such as y of 0 equals 5. An equation together with such a condition is called an initial value problem. Let's solve one. The general solution of y prime equals 2y is y equals c times e to the 2x. Now apply the condition y of 0 equals 5. Substitute x equals 0, e to the 0 is 1, so the left side is just c, and the condition says z equals 5. That fixes the constant completely, giving the unique particular solution y equals 5 times e to the 2x. One condition killed the one free constant. The pattern generalizes by order. A first-order problem needs one initial condition. A second-order problem needs two, typically the starting value y of 0 and the starting slope y prime of 0, which physically is a starting position and a starting velocity. Order in, conditions in, unique curve out. Let's make the idea visual. Picture the xy plane. The general solution y equals c times e to the 2x is not one curve but a whole family of them, and here they all are at once. For positive values of the constant c, the curves sweep upward, steeper and steeper as c grows. For negative c, they are mirror images sweeping downward. And right along the horizontal axis sits the flat line y equals 0, the equilibrium curve where c is 0. Together these curves tile the plane. Through almost every point, exactly one of them passes. Now watch what the initial condition does. We highlight a single curve in gold, the particular solution y equals 5e to the 2x. It is the one and only member of the family that passes through the gold dot at the point 0,5. That is the whole story of an initial value problem in one picture. The equation gives you the family of faint curves, and the initial condition reaches in and lights up exactly one of them. So why is this subject the backbone of science? Because nature speaks in rates of change. Start with the most famous law in physics, Newton's second law: force equals mass times acceleration. Acceleration is the second derivative of position with respect to time. So the moment you write down Newton's law, you have written a second-order differential equation. Mass times the second derivative of position equals the force. Take the simplest case, a body falling under gravity. The force is constant, negative mgc, so mass times the second derivative of position equals negative mg. Integrate twice and you get position equals negative 1/2 gt squared plus v naught times t plus x naught. There are our two arbitrary constants, and look what they are. V naught is the initial velocity and x naught is the initial position. Those are exactly the two initial conditions a second-order problem demands. The mathematics and the physics line up perfectly. To predict the motion, you need to know where it started and how fast it was going. Two more examples, and they share a single equation. First, population growth. A reasonable first model says the rate at which a population grows is proportional to how many individuals there already are. More rabbits make more rabbits. In symbols, dp dt equals k times p with k positive. The solution is p equals p naught times e to the kt, exponential growth, where p naught is the starting population. Second, radioactive decay. The rate at which atoms decay is proportional to how many undecayed atoms remain. That is the very same equation, but now the constant is negative, dn dt equals negative lambda times n. The solution is n equals n naught times e to the negative lambda t, exponential decay. One equation, two opposite phenomena, separated only by the sign of a constant. The phrase rate proportional to amount is perhaps the single most common modeling assumption in all of science, and whenever you make it, the answer is an exponential. One last model, and it is one you can feel with your hands. Newton's law of cooling says a hot object loses heat at a rate proportional not to its temperature, but to the difference between its temperature and the surrounding air. In symbols, dt dt equals negative k times the quantity t minus a, where a is the ambient temperature of the room and k is positive. The solution is t equals a plus the quantity t naught minus a times e to the negative kt. Read what it says. As time goes to infinity, the exponential dies away and the temperature approaches a, room temperature, exactly as you'd expect. And the rate depends on the gap. When the object is much hotter than the room, the gap is large and it cools fast. As it nears room temperature, the gap shrinks and the cooling slows to a crawl. That's why a cup of coffee plunges in temperature at first, and then seems to take forever to reach lukewarm. The same proportional rate idea, with a constant offset, captures it exactly. Before the worked examples, let's see our models side by side, because each has a signature shape worth recognizing on sight. All three start at the same moment on the left. The gold curve is exponential growth. The solution of dy dt equals ky with k positive. It sweeps upward steeper and steeper, never slowing, the runaway curve of an unchecked population. The navy curve is exponential decay. From dn dt equals negative kn, it starts high and falls, plunging at first and then flattening as it creeps towards zero but never quite reaching it. Radioactive material thinning out. The teal curve is Newtonian cooling. It also falls, but watch where it ends, not at zero, but at the dashed line marking room temperature A. It levels off there because once the object matches its surroundings, the temperature gap is gone and cooling stops. 3 first-order equations, 3 unmistakable silhouettes, unbounded growth, decay to nothing, and relaxation to a resting level. Learn to read these shapes and you can often guess a model before you solve it. Let's work through verifying a solution carefully, because it is a skill you'll use constantly. The claim y equals 3e to the negative x plus 2 is a solution of the equation y prime plus y equals 2. To check it, we don't solve anything, we just differentiate and substitute. First, the derivative. The derivative of 3e to the negative x is negative 3e to the negative x, and the derivative of the constant 2 is 0. So y prime equals negative 3e to the negative x. Now substitute into the left-hand side y prime plus y. That's negative 3e to the negative x plus the quantity 3e to the negative x plus 2. The two exponential terms are equal and opposite, so they cancel, and we are left with just 2. The right-hand side of the equation is also 2. They match for every value of x, so the function checks out as a solution. Notice the constant 2 and the answer is the equilibrium. If y equals 2, then y prime is 0 and the equation balances. Now a full initial value problem from start to finish. Solve dy dt equals negative 1/2 y with the initial condition y of 0 equals 100. Step 1, recognize the form. The rate is proportional to the amount with a negative constant, so this is decay, and the general solution is y equals c times e to the negative 1/2 t. Step 2, apply the initial condition. Set t equal to 0. E to the 0 is 1, so the left side is just c, and the condition force is c equals 100. That gives the unique particular solution, y equals 100 times e to the negative 1/2 t. Step 3, always worth doing, interpret the answer. We started at 100 and the quantity decays exponentially. At time t equals 2, y is 100 times e to the negative 1, which is about 36.8. So in 2 time units, the quantity has dropped to a bit over a third of its starting value. This exact equation governs radioactive decay and the clearance of a drug from the bloodstream. Same math, many worlds. Let's finish the examples with classification, the first thing you do when you meet any new equation. For each one, name the order and say whether it is ordinary or partial. First, y prime equals x squared plus y. The highest derivative is the first derivative. The unknown depends on one variable, so this is an ordinary equation of order 1. Second, y double prime minus 3y prime plus 2y equals 0. A second derivative appears, so it is an ordinary equation of order 2. Third, and watch out for the trap, the quantity y double prime cubed plus y equals sine x. The second derivative is raised to the third power, but that exponent does not change the order. Order counts derivatives, not exponents. The highest derivative is still the second, so this is order 2. Finally, the partial of u with respect to t equals the second partial of u with respect to x. Two independent variables and curly partial signs. That is a partial differential equation of order 2. The rule, order is the highest derivative. Curly partials with several variables make it partial. A little history, because this subject and calculus itself were born as twins. In the 1660s through 80s, Isaac Newton invented calculus precisely in order to state the laws of motion, and those laws were the very first differential equations, which he wrote in his language of fluxions, his word for rates of change. At nearly the same time, Gottfried Wilhelm Leibniz developed calculus independently, and we owe to him the elegant dy dx notation we still use and the word differential. In the 1690s, the brilliant and famously quarrelsome Bernoulli brothers, Jacob and Johann, solved the first great named problems, the shape of a hanging chain, the curve of fastest descent, each of which is a differential equation. And in the 1700s, Leonhard Euler turned the scattered tricks into systematic methods. A great deal of what you will learn in this course traces directly back to Euler. The lesson of the history is the lesson of the subject. To describe change, you differentiate, and to recover the quantity from its change, you solve a differential equation. Let's recap. A differential equation relates an unknown function to its own derivatives. Its order is the order of the highest derivative that appears. Y prime is first order, y double prime is second. It is ordinary when the unknown depends on one variable, and partial when it depends on several and partial derivatives appear. This course is about the ordinary kind. The single most important idea, a solution is a function, not a number, and you verify a candidate simply by differentiating and substituting. Because integration brings arbitrary constants, solving gives a general solution, a whole family of curves, like y equals c times e to the 2x. Picking out one number requires an initial condition, and an equation together with its condition is an initial value problem, which generally has a unique particular solution. And we care because the laws of change are differential equations, Newton's second law, population growth, radioactive decay, and Newton's law of cooling. Next episode, before we learn a single solving trick, we read an equation as a field of slopes and follow the arrows to sketch solutions and even compute them numerically. See you there! Today we met the central object of the whole course, the differential equation. An ordinary differential equation is an equation that relates an unknown function of one variable to its own derivatives. Its order is the order of the highest derivative that appears, so y prime equals 2y is first order, while y double prime plus y equals 0 is second order. We call it ordinary when the unknown depends on a single variable, and partial when it depends on several and partial derivatives appear. The crucial shift in thinking is this: a solution is not a number, it is a function. To solve a differential equation is to find every function that, when substituted in along with its derivatives, makes the equation true. Because integration always introduces arbitrary constants, a first-order equation has a whole family of solutions, called the general solution, with one free constant. Pinning down that constant requires extra information, an initial condition, such as y of 0 equals 5. An equation plus an initial condition is called an initial value problem, and it usually selects exactly one particular solution from the family. Why do we care? Because the laws of nature are overwhelmingly statements about rates of change. Newton's second law, population growth, radioactive decay, and Newton's law of cooling are all differential equations. Next episode, we learn to read an equation as a field of slopes and follow it to a solution. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.